this one yet. So I'm gonna be cold turkey here on this one.
Oh, that's okay. So we're gonna, oh, which one is that?
That's my oldest one. It's Tinker.
Tinker.
Yep.
Oh,
Okay.
so
You've seen
cute.
them all.
So cute.
All right.
Okay, so we're working in 1.7 now,
Now I can focus.
and this is called portion control. That's what I
Which
need
I
for my,
didn't do.
that's what I need for my food. So does somebody want to read our little opening paragraph here?
You arrive at 8 a.m. final. Ugh. And find that at least your professor was kind enough to bring donuts. Let's say she brought 4 dozen donuts and there are 24 people in class. How can she fairly distribute them? The obvious answer is 2 donuts per person. This is a very simple example of appropriation.
Yep.
Apportionation. I don't know. Yeah.
Apportionment, yep.
Yes. It's a simple example because everyone gets the same number of donuts and there are none left over. But what if some people are entitled to more donuts for one reason or another? And what if the number of students doesn't evenly divide the number of donuts? Then the situation gets more complicated. If you had to, of course, you could cut the donuts into pieces. But what if you're trying to fairly dole out computers to schools, cars, to policemen or police stations, sonogram machines, to hospitals? Half of a computer won't do any good. These items are called invisible because they can't be divided into smaller pieces. The study of apportionment is all about coming up with fair ways to divide and assign individual items. So we have to try to name something that may be apportioned other than those mentioned in the opening paragraph. Sewing machine can only be used by one person.
That's a good one. If you had to share, split up sewing machines, or anybody else have another one?
Having to share paper in class.
Paper?
So you're saying apportionment, like this is something that you can divvy up.
You can't. So for instance, like in my house, if we had to share the TVs, right? If there's not enough for everybody to get their own TV to watch it, then you got to decide who gets to watch the TV for what amount of time.
Gotcha.
Kind of like showers. We moved to a smaller home, so now it's like, well, when we first moved here and everybody was living at home, so it was like, okay, who's showering at what time? Now we kicked them to the curb. They all moved out. So, well, actually, our son's back for a little bit, but he's getting an apartment again. So thank goodness. Okay, so that's where we stand. Okay, so down at the bottom here, it says the most common example of apportionment, as we're going to see, is the United States Congress. There are 100 senators and 50 states. So 2 senators per state. That one's nice and easy. But in the House of Representatives, the number of representatives is based on the population of the state. There are 435 seats in the House, and they're divided according to population. For example, Florida has 25 seats, Pennsylvania has 19, and Rhode Island only has 2, because Rhode Island has a very small population. So why can't we just divide 435 by the population to find out how many representatives per person, then multiply by the state's population? Because it's against the law to divide politicians in pieces. So if we did that, it wouldn't come out an even number. We'd have some kind of a decimal. So that's where apportionment comes in. Apportionment is the process of fairly assigning identical indivisible objects among individuals entitled to shares that may be unequal. So it says, we just pointed out that the most logical way to attack dividing up the seats in Congress would be to divide the entire population by the number of seats. This would tell us how many people on average would be represented by one congressperson. So we call that thing the standard divisor. So we're going to learn more about the standard divisor here in a few minutes. So at the end here, throughout this lesson, we'll refer to the objects being assigned as seats, like seats in Congress, and the individuals are going to be called districts. Okay. So let's go ahead and flip the page.
Doesn't sound like fun to me.
Yeah,
It's not, as-
I like the last chapter better.
it's not as bad as it seems.
Mhm.
Oh, too funny. It's not as bad at all as it seems, so. Okay. I'm just trying to write something down quickly here. Okay, so here's our formula at the top for the standard divisor. It's taking the total population and number divided by the number of seats, and that's how many representatives per person is what it should be. But it doesn't always work out. Okay, so this is our entire lesson for 1-7 is all gonna be surrounded by this city here. So it says a large city has 20 seats to be allocated proportionally among 5 districts according to the population of each district. The population of the districts in thousands are shown in the table. So District 1, for instance, for how we read that, it has a population of 32,000. District 2 has 80,000. District 3 has 41,000, so on and so forth. And the total population of the city is 240,000. Everybody see that? So it says, explain why it wouldn't be fair just to take the 20 seats, divide evenly amongst the districts, the 5 districts, and give everybody 4 representatives.
It's because of the population.
Well, what about it?
Some areas are bigger, some are smaller.
Okay.
Just
So,
Switch district.
so you're saying only having 4 people to represent 80,000 isn't as fair as having 4 people represent 20,000, right?
Yeah.
So they should equally get a fair representation, right?
Mhm.
So bigger cities should get more.
Well, the majority of our people are from Wayne County.
Right. And so that's why we have the electoral college for our 435 seats, right? Because just because if you go by population, New York and California would get all the seats, right? And then other states would barely get any seats. So they went by population, but they also went by the farming states, right? We're called the flyover states, the Midwest states. Those states, especially like Montana, like even further west, Montana and Idaho, they have a ton of land, but not as many people. But for them to get fair appropriation, their land is being used to provide food for all of us, right? They're growing, they've got crops, they've got animals and such. And so it really started with the 13 colonies. That's where they had the original argument, because those colonies, the 13 original states, they had farming in that area too, right before all of us came about. But those 13 original states, they had farmland, and they're like, hey, wait, that's not fair. If we don't get as much representation, we don't have as many people living here because we're using a lot of our land to provide food for all of the New Yorkers. So that was kind of the argument back then for the electoral college, but it's really expanded to the whole United States because it's still true today, right? We have lots of areas of a lot of our states that are not inhabited by people because we use them for farming. So that's the premise of the electoral college. I'm sure there's way more to it than what I just said, but I'm not a history major for sure. So number 2 says, well, then let's just go ahead and find the standard divisor as we set up here, taking the total population dividing by the number of seats. So we would take 240,000 and divide by the number of seats, which is 20. And so this comes out to be 12,000 people per 1 representative seat.
Okay, so you got the 20 from a large city has 20 seats up in the top.
Yep.
Okay.
Yep, so we're taking the 240,000 people in the city and we're allocating 20 seats. So they're saying for every 12,000 people in the city. So if you look at, for instance, District 5, they have 20,000 people. So we could quickly go, oh, they're gonna barely get over one person to represent them, right? Because the first 12,000 is my one representative and then there's 8,000 remaining. So they don't even get two representatives. So number 3 says, notice that District 2 has exactly 1/3 of the population, right? 80 divided by 240. So I'm just going to write it out. 80,000 divided by 240,000 is 1/3. It would seem perfectly reasonable then for that district to get 1/3 of the seats. Why won't District 2 get exactly 1/3 of the seats? What would 1/3 of the seats be?
Oh, 1/3 of 20.
Oh, of the 20 seats.
Mhm.
Okay, because that's District 2 has 20. Oh, wait a minute.
Be 5. If you're rounding.
So District 2 has 80,000 people in it,
Okay,
and 80,000 out of the total 240 is 1/3.
right.
So they should also get 1/3 of the 20 seats. What does that come out to be?
Third, 20 seats.
$6.6
and so on.
So let's round that to 6.67.
It's 3 divided into the 20, correct?
Yeah. So why can't we have that 6.67?
Because if there is no 0.67 of a seat.
0.67 of a person.
Yeah, well,
Sometimes I feel like I'm 0.67 of a person. Okay.
because that's not a, what do you call it? A
It's not
proportion.
divisible, yeah, so we
Right.
cannot have part of a person. And I'm gonna put parentheses seats so to remind ourselves. Remind ourselves, the seats are the objects. Representatives. Everybody with me so far?
Yep,
Yeah.
Okay. So let's go ahead and flip the page. So it says, well, we've seen that you can't assign seats simply based on what percentage of the total population a given district has. That percentage still plays an important role in apportionment. So we're going to explore that role here below. We're going to go through the solved example here. So part A says, describe what this calculation represents in apportionment problem. So we've got our population of the district. So the city population divided by the total times the total number of seats. It's kind of like what we did here, right? On District 3, we said 80,000 divided by 240. We got 1/3 of 20, and we said it was 6.67. Now, if we look at B, it says simplify this fraction. Population of the district divided by the standard divisor. What can you conclude? So let's break down what we know about the standard divisor. So down below, it gives a solution here. So if we take the population of the district divided by the standard divisor, that's the same as saying the population of the district divided by this fraction, because we just defined the standard divisor as total population divided by total number of seats. So it actually comes down to this right here, which is a number divided by a fraction. So population of district divided by this fraction, we're not gonna ever have to do this by hand, so that's why I'm kind of just briefly going over it. Is a number divided by a fraction, you're gonna use KFC. So when you divide by a fraction, divided by a fraction, you keep it. You keep the first fraction, so population of the district divided by 1. And then you flip the second fraction. So see how total population over total number of seats. Now we have total number of seats over total population. And then you change it. So you change your division to a multiplication. So we have the division bar, now we have a multiplication. And then when we multiply these together, we get the population of the district times the total number of seats over the total population, which is exactly what we had in part A. The population of the district over the total population times the total number of seats. So it's basically the same thing. A little bit to contemplate, but don't worry, your brain's going to be thinking about it as we work throughout the night. We're not going to be doing any of this by hand. The rest is going to be using Desmos to build the concept. Okay, so let's flip the page. And we're going to kind of write about this. So it says, perform the calculation in part B of the solved example for District 3 in our example problem. Then write a description of what the result of the calculation tells you. So for District 3, we're going to write this. The population of the district, which is 41,000, divided by the standard divisor, oops. And that comes out to be, I think it's 3.67, but yeah, 3.42.
Okay, I am lost. Where did you get the 41,000 over the 12,000?
Okay, so they said to use what we did in part B on the past example.
Okay,
So part B is the population of the district,
right.
which on page 108 is 41,000.
Oh, okay. See, I keep forgetting that's 1,000. Okay,
And then we're dividing by the standard divisor, which we said it was 12,000 people per representative.
okay.
So the 3.42 is 3.42 seats for District 3. And again, we can't have 0.42 seats, right? We have to figure out some way to decide who's getting the bless you, who's getting the extra and who's getting a little less. So it says to summarize the formula from question 4, which is the percentage of the total population that lives in a given district multiplied by the total number of seats, is the theoretical number of seats that each district would get if it were possible to hand out fractional part of seats. We're going to call that the standard quota. So this is their standard quota for District 3. So we can find that by taking the population divided by the standard divisor, just like we did up here. So number 5 says, find the standard quota for each district in the city described on page 108. So the 5 districts that we had here back on 108.
Mhm.
And I suggest that we make a little table. So I'm going to write district. And then I'm going to write population because I'd like to kind of keep track of that. And then I'm going to do standard quota. Everybody with me so far? So I kind of just made a little table here. I hope I'm recording. Okay. And then I'm going to fill in the population. I'm just going to remind myself that these are in thousands. Okay. So I'm going to show you by hand for the first one, the standard quota, and then I'm going to go to Desmos. And I've already, I will put a link of all the Desmos work for 1.7 in our recording in JetNet. So it'll all be there for you. So today, if you just want to follow along with what I'm doing, if you want to join me to do it, that's fine too. But the first standard quota is going to be taking, actually, we already found District 3 up here, right? Because they had a population of 41,000. Divided by the 12,000 standard divisor, gave them 3.42. So this one is 41,000 divided by 12,000 is equal to 3.42. So the first one is going to be 32,000 divided by 12,000. And that one comes out to be 2.67. I'm going to give you the rest here. This one's going to be 6.67. I'm going to show you how to do it in Desmos. We're going to put the rest of our work. 5.83. And then this is 1.67. Okay. I'm going to go to Desmos, and you'll see these values come out for the standard quota once I get to Desmos too. So don't fret. So in Desmos, I'm going to make a table just like I kind of made there, but it's going to look a little different. So I'm going to say my plus symbol here, and I'm going to choose table. And so I'm going to type all of my populations here. So 32,000, 80,000, 41,000, 67, and 20. Whoops. That's what I meant to do. Okay. 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 So then up here, I'm going to delete the Y1, and I'm going to say I want to use X1, and I'm going to divide by 12,000 because we said that's how we're going to get that value. So all those rounded decimals to two places should be what we wrote on our paper: 2.67, 6.67, 3.42, 5.58, and 1.67.
Okay, and you put X1, would you put up there? I can't quite see it.
So I named my column of population X1.
Oh, gotcha.
I
Okay.
want to take that column and divide by 12,000. So
Okay.
I'm giving it a recipe.
Okay.
Yep. Everybody with me so far?
Mhm.
Okay, so we're going to kind of keep that handy. We're going to go to page 111 for a moment. And I'm going to go flip back to my page 111. So it says, now that we know how to almost find the number of seats that should go to each district, the rest of the study of apportionment is about deciding if each district's number of seats should come from rounding its standard quota up to the next bigger whole number or down to the next smaller whole number. Seriously, that's pretty much it. A logical place to start is by simply using familiar rounding rules. So we're going to give it a try. So number 6 says round each of the standard quotas you calculate in question 5 to the nearest whole number. So use your regular natural rounding rules. Then add the results and explain why that won't work as the number of seats assigned to each district. I'm just going to go back here to the table we made, and I'm going to use my rounding rules. So using natural rounding, would we round this first one up or down?
Up.
So we'd round that up to 3. What about the next one?
That'd go up as well.
Yeah. What about the next one?
Down.
So 3, and then the next one?
Up.
And then the next one.
Up.
So if we add those, what do we get?
10, 16, 20. And that's exactly how many seats we were supposed to have.
Do we get 20?
Yep. If that's it, I mean, if you're counting the seats, 3, 7, 3, 6, and 2, 20.
I come up with 21.
Wait a minute, did I do this wrong myself? And
3, 7 is
3,
10.
2, and then 6 and, oh, you know what? I wrote down the wrong number. I put 2 and 2 instead of 3.
There we
That's
go.
why I was coming up with 20.
So we have 21. So why won't that work?
Because we only have 20.
Okay, so we only have 20 seats. But we are trying to allocate 21. So that's not going to work, right? We got to get rid of one. Somebody's got to give, somebody can't round the way that they're supposed to round. Is everybody with me on that?
Mhm.
Okay. So this is not, to me, this is all things that make sense. It's just things that you've never really thought about and went through before. So that's why it seems a little quirky. So question 6 shows that simply rounding each standard quotient to the nearest whole number isn't a reliable method of apportionment. This realization dates back to at least 1790, when both Alexander Hamilton, the first Secretary of Treasury, and Thomas Jefferson, hopefully you know who he was, the president, right? They came up with some different ideas, and they were kind of arguing about like, how are we going to take care of this? So the methods of apportionment that we'll study are all based on first calculating the standard quota, which we did, then deciding whether to round up or down. For any district, the lower quota is the result of rounding the standard quota down, and the upper quota is the result of rounding up. So in 7, we're going to fill in those standard quotas we just came up with, and then we're going to round them all down for the lowers, and we're going to round them all up for the uppers. Okay. So we've got 2.67, 6.67, 3.42, 5.83, and 1.67. So the lower quota is basically just getting rid of the decimal, right? 2, 6, 3, 5, and 1.
I thought number 4, I had written down 5.87, not that it matters that much.
It's 5.83.
Oh, I had 7 on there. Boy, I'm not doing so great.
Let me go back to the decimals and just make sure. Oh, it's 5.58.
Yeah, that's what I had.
I thought you said 5.7.
No, I didn't. I did have it wrong.
I had it wrong too.
What might make our answers different, right?
5.58. Oh, I know, and I've done this 3 times already in the last 2 days. So you
Well,
think
no wonder, golly.
problem is that, yeah, I start to rely too much on my
Yeah.
up here. My noggin isn't as good as it used to be.
Here. I mean, I'm talking about me.
Okay, so thanks for the correction. So 2, 6, 3, 5, and 1. And then the uppers are just going to be one more than the lowers. So these would be 3, 7, 4, 6, and 2. How's everybody doing so far?
I have a question on 3. Why would you go to, if it's lower? Okay. I see. 6.
So the lower and the upper are just, if we were to round them all down, what would it look like? And if we were to round them all up, what would it look like?
Okay.
Yeah.
All right.
So we're just proposing the 2 different options.
Okay.
So now on page 112, it says the first method we're going to study is Hamilton's method, which was approved by Congress for use in 1791, but was never actually used since President Washington vetoed the bill. But we're going to go through it. So Hamilton's method says assign each district the number of seats according to its lower quota. If this adds to the right number of seats, you're done. Fabulous. Let's do that first. So if we add just the lowers, what do we get? 20. Get what?
You end up with 18, right? 6, 9, 11, 12, 17.
17. So we don't have enough, right? We have 3 extra we got to give out.
Right.
Okay. So step 2 says, if it does not, assign extra seats one by one to the districts in descending order of size of the fractional parts of their standard quota. So the decimal part. So for example, if 3 districts have standard quotas right here, 2.93, 4.7, and 3.15, the first extra seat would go to the district with fractional part 0.93 because it's the highest decimal part. And then the second would go to 0.7 because it's the next highest decimal part. So use Hamilton's method to apportion the seats for the city. We've done most of the work already. Make sure you clearly write out how many seats each district gets. A table wouldn't be the worst idea ever. And I'm just going to go back to this. I'm going to use the table we already have going. So we have 3 extra to give out. So let's go to the decimal parts. So who's the first one that should get one of the extra 3 seats?
Well,
You're muted.
3 of them have 0.67 for decimal.
Isn't it number 4? Because it's I thought it was 83. Is it
Oh
wrong?
no, we discovered I misspoke. It's 5.
5.8.
You know what?
5.58.
Let's just double check it again. I've done this. Yeah, 5.58, Darla. Sorry, I made that mistake. We just found it.
5.8.
Yeah.
Okay, then it's the 3 of them with the 6.7.
So the 0.67, 0.67, 0.67. Okay.
Correct.
So those 3, I'm going to circle their upper quota because they're going to get rounded up because they have the highest decimal part.
3, 7,
And the 6.
3, 5,
Oh my
2.
gosh.
Yep.
The 3, the 7, and the 2, and then these 2 don't, right? The 3 and the 5. We have to
Correct.
use their lowers. So we have 3, 7,
7, 3, 5, 2,
and that adds to 20.
20.
Okay, so that's Hamilton's version. Are we following so far?
Yeah.
Okay.
I'm
So-
scared. It's still making sense.
That's good.
Yeah.
So it says the apportionment method that was adopted by Congress after Washington's veto in 1792 was designed by Thomas Jefferson. And shockingly, it's called Jefferson's method. It's a bit more complicated than Hamilton's method. It uses what we call a modified divisor. The idea is to make sure that every district gets its lower quota. We know that won't work in general because usually the number of seats will add up to something less than the correct total. In Jefferson's method, we'll make the quotas get bigger by making the standard divisor lower. So, and I'm going to show you through Desmos so you can kind of see how that's going to work. So down below, so how Jefferson's method works is we assign each district the number of seats according to the lower quota, which we've done. If this adds to the right number of seats, you're done. If the sum of the lower quotas is less than the number of seats, choose a modified divisor that is less than the standard divisor and recalculate the lower quotas. Use this as the apportionment if the lower quotas now add up to the total number of seats. If not, adjust the modified divisor again. Okay, so, so number 2 says, recall that the standard divisor calculated before was 12, right? Or 12,000. So let's just remind ourselves that it was really 12,000. Fill in the following table, in each case, getting the modified quota from dividing a district's population by the modified divisor of 11, or 11,000. I'm gonna go to Desmos to do this. So you're gonna see, this is the cool part about Desmos, is I can do it right next to the one where we did the 12,000, and you can actually see it change. So we can say X1 divided by 11,000.
Okay, I don't know how you got that to work.
So go up here and just click to the column next to it.
Okay, I still didn't get it.
Your column didn't click next to it.
Well, I don't get any of those numbers. I mean, I put in the 32,000.
Okay, you put in the column,
Yeah,
and then you're gonna go to where yours might say a Y1.
I changed it.
Okay, so now it's gonna say X1 and then divide by 12,000 was what we did before. And now in the new column, you're gonna say X1 and divide by 11,000.
But it didn't do the math.
Did you hit enter? It didn't do the math? You wanna share your screen, hon? I'm gonna step.
No,
Oh, you got your thing,
Sure.
right? Darn it. Let's see.
that's okay. What did I do wrong?
Let me see. It doesn't look like you've done anything wrong. Let's try it again. Delete your X1 divided by 12,000 and see.
Okay, delete. And then I just want to know how to do it, because if it's on a test, I have to know how to do that correctly.
Yeah, and you know,
Yeah.
usually on the midterm, I don't know that we'll have you do a whole big problem, because if you make one mistake, right, kind of throws everything else off. So we might give you a chunk and say, what would you choose between these two using Hamilton's method? What would you choose between these two using Jefferson? So there'll be pieces, but you still need to know how to do the concept.
Yeah,
Did that work?
no, I'm just gonna start over.
Can
So-
you, yeah, I just lost mine again.
Go to table.
Yep, so make a new table,
Yep,
and then in X1, or what did yours come out to be, X1?
yeah,
Then just type the numbers, 32,000, 80,000, 41.
and then I left the other one alone. And then I have to press the divide button.
So the other one should say X1, not Y1.
Well, it says Y1.
So delete the Y1.
Oh, gosh.
That
This is
might have been
wrong.
an issue, because you have to tell it you're using X1, that column. And you
Okay,
divide that count,
so I just type in X1.
X1, and then divide your divide symbol by 12,000.
No,
Where is your table symbol? I've been clicking on all this stuff. and I'm
it's
not-
on the little plus sign.
The plus button is a
Oh,
menu.
okay.
See?
Oh, wait,
let's see.
let me stop sharing so I can see again.
Let me see.
Okay, hold it up
To
again.
make sure. There it is. I did exactly as you told me, and I got the exact same thing.
Well, click on the exclamation point in the triangle. It should tell you what's going on.
It tells me it's too high. Too many variables. Try defining X negative underline 1.
So maybe you have too many X1s. So maybe go to the first column that says X1 and call it a C.
Go to the first one.
Yeah, delete the X1 in the first column and call it a C, a different letter, and then go
Okay.
over to the right column and change that X1 to a C.
Okay. Let's see, 1.
And let's see if it
I
works.
lost all my numbers now.
Oh, no.
It's okay.
32,000,
Yep. As soon as,
80,000.
nope, it doesn't like either one of those, so. Oh, well,
Let's see it again.
it wouldn't let me do anything.
Yeah, mine, when I tried to put in the X1 and then the divider sign so I can put it underneath, it deleted both columns on. Is that what it did to you, Darla?
Yes.
Yeah, I don't know. It did it to me too.
Let me see. So when you started, you just hit the plus sign and then you hit a table.
Yep.
Yeah.
And then when you hit a table, did you get like some kind of a color here with dots? You should have some kind of,
I don't have a color. I have a black dot. You
Yeah,
got a
I-
black one, so yeah.
Yeah.
oh, you just have a solid black dot?
Well, if you scroll up, yours is solid black too.
Oh, it's got black with white dots, so
Yeah.
Yes. That's
yours
what mine
isn't
is.
solid?
No, I got the
Okay.
exact same
Okay.
one.
So then let's try it again. Let's try, don't put any commas. Are you putting commas in?
No.
Okay,
No.
I just want to make sure. I'm just throwing out possibilities here. So let's just do 132,000.
Hmm.
And then now yours should say X2 and Y2.
Well, mine says X1 and Y1, but okay.
I don't know why yours keeps, because usually it'll generate the next one. Do you have a table up above it still from what you did before?
No, I deleted it because it froze up on me.
Okay, so then go over here to the where it says Y1 and delete that.
Okay.
And then I'm going to say X, and I'm just going to put a 2, and it should make it a little 2.
See, when you do that, that's what made my columns both disappear.
Well, right, but now you have to actually tell it because I'm not doing any action. So it's like, well, you just got X2 at the same spot. So I'm gonna say divided by, and that you use your fraction bar, right, to do divide,
Mm-hmm.
and then 12,000. And now as soon as they start typing 12,000, it does the calculation.
Oh, got it.
Okay. Now how'd you do that?
So
Uh,
I went up here and I said
Well-
X, in the second column, I put X2,
okay. I think.
and then I
that's
got
my
2
problem.
exclamation points because I don't have a calculation yet.
Let's see if I put in another number. What is it? 80,000. No.
Okay, I want you to follow what I'm doing and just watch all my actions because I think I know what might be happening. So I'm gonna go here, I'm gonna start a table.
Yep.
So right now there's an X2 and a Y2. Yours is gonna be an X1 and Y1.
Okay.
So I'm gonna just do one number, 32,000. That's all I'm gonna do there. Then I'm gonna move my mouse. I'm not gonna touch the 32,000. I'm just gonna go click up on the Y2. Don't touch any of yours because you're gonna.
Nope. I'm watching.
Okay, because when you look away, I think you're missing what's happening to my screen.
Oh, because
So-
my hands are right here.
Okay, so now I'm gonna change that Y2 to an X2 because I wanted to use what's in X2. And
Okay.
notice it gives me an error, and that's okay. And my number went away. I'm not gonna go back and type 32,000 again. It's gonna pop back up.
Okay.
So while it's doing this, I'm gonna then just press my backslash for my divide. And then I'm gonna type
Okay.
12,000. And then it's like, okay, now I'm gonna use what's in X2 to calculate the next column. So I think maybe you were going back down, you're like, oh, my number went away, and you put a number back in there.
Let me see.
I'm wondering.
I will try it one more time.
I know it's hard when I'm not right there with you to like try to.
Oh,
catch
you're fine. Okay, so I got that. So
A lot of this is, trial and error.
32,000, and then I'm gonna go over here, change this to X1,
Mhm.
and then press my divide. I'm leaving the other number alone,
Yeah,
and I gotta press enter.
well, you don't even have to press enter. As soon as you change the X2, as soon as you change the Y1 to X1, it should give you 2 triangles with exclamation point.
No, I did exactly what you showed me.
Okay.
Oh, frustrating.
Go back.
Can you share her screen?
No, because I'm doing it on my iPad.
Oh, that's,
So go back. So we're gonna start a new one. You're gonna walk through exactly at the same time I'm gonna. You're gonna start a table.
Table.
And you're
X1
gonna-
is there. You got
You're gonna
X2,
put in
that's
one
fine.
number, 32,000.
32.
Don't hit enter. Just grab your mouse.
Nope. I just typed it in there.
Yep, grab your mouse and go up to where it says Y1, mine says Y2,
Yep.
and then hit backspace, backspace.
Okay.
And then I'm gonna call mine X2, but you're gonna call yours whatever yours is over here, X1. or
Right.
whatever. So now I have 2 exclamation marks.
Yeah, and the square and the red triangles.
Mm,
Does yours look like mine?
no, I've got the blue thing.
It has something to do with the X that you're using then or something.
What
So
other
stop-
X is there?
I don't know. Stop. I'm gonna stop sharing. I want you to show me what you have right now. Because it's something going on with that one step.
Okay, well, I did this part.
Yeah, so now type X1,
And I'm just typing it off my key, X.
1, and then don't hit enter, just leave it there, X1.
No. Oh, hold on. Come on, work. Okay. Back.
The other thing that might be going on is, are you using a downloaded Desmos? Or is it like the internet version?
Might be the downloaded one. I don't know.
I don't know. Did it not do it that time? Let's see what it looks like.
Well, I don't know what I did differently.
Yep, that's right, that's right, that's what you want.
Yep.
Yeah.
So
And
now
then I'm
don't-
gonna type in
don't-
my 12.
No. So now leave it like that. Now let me show you mine real quick.
Okay.
You're at the exact right spot. So I'm like, no. So now
Well,
up in that second column where you just put the.
Oh, you gotta
X1,
divide.
Now you hit divide right there. And type 12,000.
Divide.
And your color thing should pop back up and you should,
Yay, it's working.
yay,
Oh my gosh.
we persisted.
Mhm.
Okay.
I was
Yes,
like, I
I have
am
the
not
exact
giving up
same
on you, Darla, no way.
Man.
So now you can just fill in all of your other
Yes.
80,041 and it will calculate automatically.
Yep, I see that.
Yay.
41. 67. And then 20.
Okay. This is so exciting. That just made my night.
Yeah. I'm gonna have to turn a light on if it gets any darker.
Me too. I have lights on actually. So do you have the same numbers I have here then?
Yes.
Okay, now I
Well-
did a second column, the same thing, type X1 divided by 11,000,
Oh, okay.
because now we're gonna change our divisor.
So X1 again.
Yep, because you're still using, you always want to use the first column and then you're gonna divide that first
X1.
column by
and then
11,000.
Divide 11.
Mhm.
It's working.
Yay. Okay, so we're gonna fill in the modified quota. So 2.91.
Oh. Go back to what we were doing, right?
Yeah, 7.27, 3.72,
Page.
actually 3.73, but it doesn't really matter. 6.09 and 1.82.
So this is our modified.
Yep, because we're using a different divisor. We calculated originally at the beginning of this lesson 12,000, but they said we're going to use something smaller so that our numbers round up.
2.91.
Mhm.
And then 7.27,
Mhm.
3.73,
Mhm.
and then 6.09
Mhm.
and 1.82.
Mhm.
Okay. Whew.
And so now it says modified lower quota. So again, we're gonna not use any of the decimals and we're just gonna use the whole number that's there. So the lower number, if we were gonna round them all down. So 2, 7, 3, 6, and 1.
19.
Ugh, so they round to 19.
No, that's 10, 16, 17, yeah, 19.
Right. So no, not enough, right? We need to allocate 2 more.
2.
One more.
One.
I'm sorry, 1 more. I keep thinking 21 to allocate 1 more. Okay. So on the next page, they're going to say our next attempt will be to change the divisor we're using. Do you think we should make it bigger or smaller than 11,000?
Well, if we're short, then we do need to make it bigger. Where am I at? Where are you at? Okay, cool.
So we started at 12,000.
Right, okay,
We lowered to 11,000. We're getting closer because at 12,000 we allocated 17.
right.
At 11,000 we allocated 19.
So then go down, smaller
So
than.
we need to make it a little bit smaller so that our numbers, we need 1 more of the districts to bump up, right? So we get to 20. So they're
Correct.
telling us to go ahead and do it again, but with 10,500, 10.5, 10,500. So the cool thing is we can just go to Desmos,
X,
and I'm gonna make a 3rd column here.
1.
That's X1 divided by 10,500. So we're gonna fill these in 3.05.
So you always do round them up then.
So the modified,
I round to my nearest second decimal, 3.05, 7.62,
right,
3.90, 6.38, and 1.90.
7.62,
Mhm.
390, and 6.38, and 1.9.
Mhm.
Okay, in the lowers, so. Hey, that does it.
Yep. So we should get 3, 7, 3, 6, 1, right?
Yes, 20.
Yay. So the last one is a little bit different. It's called Webster's. And so it says Jefferson's method was used in Congress until 1842 when it was replaced with a new method devised by Daniel Webster. He was a distinguished congressman, senator, and 2-time Secretary of State. Webster's method also uses modified divisors, but is based on standard rules of rounding rather than lower quotas. So Webster's method is assign each district the number of seats by using the standard rounding rules on the standard quota. So rounding up if it's 0.5 or bigger, and rounding down if it's less than 0.5. If the sum of the seats is equal to the number of seats available, use this as the apportionment. If not, modify the divisor and try again. If there are too many seats assigned, use a larger divisor. If there are too few seats assigned, use a smaller one. So we've already started doing that because if we go back to number 7 here, if we use our regular, wait, back to number 6. So if we use a number 6 here, if we use our regular rounding, this would round up, up, down, up, up, right? And so we'd have too many. So going to Webster's here on number 6, it says we already know from question 6 that we would get 21 seats. So we can skip right to step 2 in Webster's. It was 1 too many. So instead of at 12,000, we need to go a little bit higher, right? because we need one of those to round down this time. All the other two methods, we were trying to get up to 20. Now we're trying to go from 21 down to 20.
So now we
Um,
have to do 12.5.
Yep. So they're saying try 12,500.
Oh my, they don't want much, do they?
So I get, that's not making sense to me. If the one we used was too high, why would you go 12.5?
Because when you're dividing by something bigger, so it makes everything round down smaller.
Oh, gotcha. Okay, now that makes sense.
It's kind of a weird concept.
Yeah.
Okay, so I'm gonna bring up I'm gonna start a new table here.
I just added to it.
You made a fourth one?
Yeah,
Will it let me?
yeah.
Oh, I didn't get that to do that this morning. I didn't go over. So X1 divided by 10 or 12,500, right? Okay,
Yeah, and the numbers come out.
yeah. So we've got 2.56, 6.4, 3.28, 5.36, and 1.6.
You still hanging in there, Melissa?
Poor thing.
What is it? The second to last one is a 5.36?
Yep.
Because I'm watching your guys's. I'm not having mine on here and make it too confusing, all three of us trying to do it.
Melissa said, yeah.
Okay.
Okay, so I'm gonna go back to my paper here so everybody can see. So this is what it came out with 12,500, and we're gonna use the regular rounding rules. So this one's gonna round up. This one will round down. This one will round down. That one will round down to 5. And that one will round up.
19.
So we're at 19. So we're one short. So we need to go somewhere between 12,500 and 12,000, right? We went up too much. And now we need to add one more back on the 19. So I'm going to tell you, just to save time, if we do 12,250, it works. And we can go to Desmos. I know you guys are troopers hanging in there. So I'm going to go over and see if I can add another one. I can. Yay. X1
Yeah.
divided by
So
12,250. And so this goes to 2.61, 6.53. So it gets District 2 to round up. 3.35, 5.47, and 1.63. I'll share my paper again. So now that one rounds up, this one rounds up, that one rounds down, that one rounds down to 5, and that one rounds up to 2. Yay, so we get 20.
7, 3, 5, 2. Isn't that what we did before?
Yes, but it was just using a different method. So
Oh my gosh.
I know. So the ordering, it doesn't matter on the ordering, but if you kind of want to, if you're remembering the ordering, we started with Hamilton's, it goes in alphabetical order, H, and then goes to Jefferson, and then W is Webster. The worksheet, I'm asking you to kind of go through these again. If you want more practice, I'm reminding everybody at home, I will have this recorded sometime this weekend, hopefully tomorrow I'll have time. And in addition, you could go through the did you get it? The did you get it from the beginning of lesson 1 in the orange, they take you through a new scenario all the way through, just like what we did, Hamilton, Jefferson, Webster. And the cool thing about the did you get it, if you haven't noticed, the answers are all at the back of the lesson. So the answers for all of this 1.7 are right in the portfolio section
Wow.
here. Down at the bottom, here are the answers to the did you get it. So if you want to go through and do a practice problem, go to the first did you get it, and it's going to have you kind of basically walk through. It's a new town with different populations to allocate. Yep. And I believe, actually, if you didn't throw away the Math 040 worksheets, I'm not collecting it, but I'm saying if you didn't throw yours away, one of the worksheets I created in there was the did you get it? So you'd have it on paper to actually write out. But if not, you can just use scrap paper.
No, I kept all mine.
Well, then you can use it.
Yeah, they're still in there.
So if there aren't any other questions, I'm gonna let you all go because I feel that I kept you over.
It's
Okay.
okay.